All right, cool. So we're going to talk about using SQS as an event trigger. Just in case you don't know where you are, that's what we're going to do. My name is Rory Richardson. I'm head of development for Serverless. This is Lue.
I'm Lue Kawasme. I'm the engineering lead for SQS.
All right, so what we're going to do is I'm going to kick it off with talking a little bit about, well, why this particular technology combination is so important. And then we're going to dig into a little bit of how a customer has applied the technology. And then I'm going to hand it off to Lue to look a little bit under the covers and talk pretty deeply about how this stuff actually works. So I'm going to start off by going backwards and give a short history of the messaging broker, because it's kind of a weird thing when you think about it. I mean, back in the day when we were using mainframes, how many of y'all ever touched COBOL or used a mainframe? All right. So when you were allocating vCPU at the function level, when you're writing COBOL, the messaging broker was critically important for how you were triggering the functions. But then mainframes sort of went out of fashion, and we started building these monolithic applications where maybe the messaging broker wasn't nearly as important because it was all contained within one structure. But now we talk a lot about distributed systems. So the evolution of modern messaging brokers has changed a lot over time, right? From where we were doing on-prem and managing the brokers ourselves, maybe it was in the mainframe or on the server farm, all the way to achieving higher scalability and reliability. And then now we use the messaging brokers to automate, to innovate, and drive event-driven architectures. But if you think about how this came about, or why we have developed SQS and Lambda the way that we have, I kind of have to start with the story of the two pizza teams. How many of you have heard the two pizzas team story? Because we tell it a lot. Right. So two pizza team, great idea. This is how we're going to release more great code, because we're going to decouple our monolithic applications into event triggers and create microservices. And back in the day, we called it service-oriented architectures or two pizza teams. And that's a fabulous story. Marketing loves that story. It involves the word pizza. But it isn't exactly the whole story from the technology standpoint. First of all, we saw the rise of the API. I mean, internally, in order to define the two pizza team, we had to define the team by the API definition. Awesome. We had 4 to 6 individuals defined their work and resources by the API definition. Cool. This is an awesome idea. So who's actually triggering the API? Do we have a two pizza team for that? Who's managing the messaging broker? So this was the rise of how we were thinking about the messaging broker slightly differently by moving our teams into distributed systems. Now remember, 2001, 2002, we didn't have the cloud. We didn't have a lot of things back in 2001. What we had was a business problem that we wanted to release code faster. Then we made a people decision to make smaller teams more accountable for the full life cycle of the code. And then we had to come up with all the mechanisms and technology that aligned to that strategy so we could get to 60 million code releases per year now. So when we're building with microservice, serverless is a really good natural fit. Because if your microservice is decoupled and it's completely event-driven, why should we pay for anything when we're not using it? Instead, if we could make these architectures completely event-driven, well, then the pipe dream, the holy grail, was what if our infrastructure costs could be linearly related for the business that we're having to come in? All right, well, that's a cool idea. That way, we're only paying for value. We are able to scale fairly automatically, and, well, there's no infrastructure to provision or manage. How many of you have ever had to manage the messaging broker? Yeah? Not? Was it an awesome job? Did you really yeah, messaging broker? Probably not. I mean, managing the messaging broker is actually a really tough job. The messages have to be, well, deterministic. Can't lose one because it is the nervous system of your infrastructure. It has to scale almost infinitely and unpredictably because how those messages are being sent internally. It kind of has to be cheap because no one really cares. This is not the secret sauce of how you're driving your business. So, do any of you know what the first service was that we released on AWS? Very first service. Yeah, exactly, SQS. Well, now that you think about it in terms of the two pizza teams, it kind of makes sense that we wanted a cloud-native, scalable, elastic messaging broker because this is the nervous system of any distributed architecture. Another thing that is really important to understand about why you're in a couple SQS with Lambda is the idea of asynchronous programming. If your Lambda is programmed or written in a way that it is waiting for a call to come back, well, that's idle CPU. The whole idea behind a function as a service is that you don't have to pay for CPU that you're not actually using. Do any of you happen to know this CPU consumption of a data center that you're using today, or even across EC2? Probably not, because we're not thinking that way. We provision a server, and we never over-provision a server. We always under-provision. So effectively, you're paying for resources that you're not using. With a distributed, completely event-driven network, this becomes a lot more efficient. So once we released this last year as a feature that SQS could trigger Lambdas, it has now become the #1 event trigger for Lambdas. And a key driver of that is asynchronous programming. So we do about 25 billion messages per hour with SQS. That's about 500 billion messages per day and more than 3 trillion per week. So we're built for scale. We're built for resiliency, and we're built for high availability. And that's why we think that SQS and Lambda are really better together. SQS isn't the only thing, of course, that's triggering Lambda. We support the invocation integrations amongst all of these services, and you'll continue to see this list grow over time, because at the end of the day, we would like to see, well, Lambdas being able to be triggered by just about anything. All right, so let's talk about a real use case of customer who's actually integrated SQS as an event source for Lambda. How many of you have actually done that integration already and are using SQS as an event source? Awesome. This part of the presentation is super boring for you, and I bet you can't wait to talk to Lue. So Airbnb built Stream Alert in order to stream and create alerts at scale. And it can handle terabytes of information with this architecture. It's open source. This is Googleable. You can find all the information you want on Stream Alert. And if you notice, SQS is used in 2 places within this architecture. Oop. Oh, let's go back. All right, this is the button I wanted. All right, up here, can you see that? I know it's really small. Forgive me, don't put it in the survey. I know it's small. So if you're using SQS up here, we were using it to trigger the Lambda in order to initiate partitioning. What's even more interesting, in my opinion, is the use down here, where SQS is being fed into by Lambda in order to classify and normalize the message. And then the messages are queued here, and then triggering a Lambda for the rules engine and threat intel. This putting SQS here between these 2 Lambdas means that you have a buffer for how the messages are being sent. And this is why this is a great architecture for scalability. Now, with that, I'm going to hand it over to Lue, and he's going to get started with how serverless message processing actually works.
Thank you, Rory. Hi, everyone. How's your reInvent going so far? Woo? Good? OK, super. So Rory walks in a room, and the energy level always goes up. And I'm seeing a little bit quiet here still. So we're going to talk about SQS and Lambda. Just as a show of hand, how many people in this room have used Lambda? OK, super. And how many have used SQS? And together? OK, that's a very nice combination. So what we're going to do today is dig deeper into how we've actually architected SQS triggers to Lambda, and go as well into some tips and tricks when you're doing your own integration and you're using that. But before I start there, I'd like to talk a bit about this integration pattern. Enterprise integration patterns have established themselves as kind of a common lingo between developers when they are doing integration projects. And in this particular pattern, which is the pipes and filters patterns, usually an event starts on one side, whether it's originated from a system or by a user clicking on your website, and then travels through a pipeline. As it's going through the pipeline, that event is getting either enriched, you're adding more data to it, or you're using the attributes of that event to branch and maybe trigger multiple pipelines, like if you're in monitoring a stock trigger or monitoring something, you might want to have an audit trail of a pipeline that is recording everything that happened, and another pipeline that is acting on the actual stock ticker information. So to implement that pipeline using AWS tools, one of the patterns that we've seen our customers doing a lot is starting with SNS that allows you to do filtering and branching. So you publish a message into SNS. Then based on the rules that you can set there, you can trigger multiple pipelines and go down, include SQS, put the message in a queue to act as a buffer for you. Then trigger either your own Lambdas or have your own Polar fleet that can pull from SQS and they trigger a downstream, store the data in a downstream database, whether it's RDS, Aurora, or whatever your storage service that you're using. So I'm going to focus now more on the SQS and the Lambda component in that architecture. So messages start coming. You push a message in a queue. Messages get stored durably there. They can stay there for the full retention period of 14 days. By default, it starts with 4 days, but you can configure that. We've implemented a polling system that looks at your queue and always monitors what's in it. So the Lambda starts pulling from that, and you configure your function. It will go trigger your function. It will pull the data in batches and hand it over to your function. So that's the simple story about that. Once your processing completes, Lambda will send back to the queue and say, OK, now I have finished working on this payload, and I'm going to delete the message from the queue. And this is very powerful. Like this deletion or acknowledgement after you process your load is very powerful, because now I know that I've processed my Lambda successfully, and then I don't need that payload anymore. But before that, that payload is very useful. So if my function fails, I still have access to that data. And in fact, SQS will replay that again for you. So looking at both sides of the picture here, on the left side, we see the message processing. All messages are stored durably for you. The queue can accept the messages at any rate. So whether you're doing 5 TPS, 100 TPS, millions of TPS, you can just trust that SQS will be there for you. You don't need to provision any capacity here on both sides, whether it's on SQS or on the Lambda side. Like internally, we monitor how much traffic you're using in your queue, and we'll decide how much storage node we're going to keep for you. And every message gets stored in 3 hosts across a minimum of 2 availability zones. So that's how we guarantee for you resiliency here. If an availability zone goes down, or you don't have access to reach that for whatever happening, someone is digging a tunnel and just decided to cut a fiber, you don't worry about that. Like, we'll start delivering the messages from a different availability zone. The Lambda will start pulling those messages, and it will pull it in batches to guarantee better utilization of your Lambda function. One of you might think, well, I've used before SQS triggers to Lambda, there was something called async invokes of Lambda. In fact, internally, we use the same architecture. We built a queue to make it also easier for you to use async invokes. So you can fire things at any rate that you want, and then asynchronously, and then we will invoke the Lambda on your behalf. But there are slight differences between both. Like with async invoke, it's a direct integration. With SQS and Lambda, you'd have to manage a couple of resources. Like you need to know about your queue, and you need to know the Lambda one. Both of them scale automatically, so you don't have to worry about the scale. In fact, we built it in a very similar architecture. The async invoke doesn't support batching. With SQS integration to Lambda, you see batching. Another one is the DLQ policy. You can configure dead letter queue policy, where if my function fails, what happens to that message? You can configure multiple retry. With the async invoke, there is very limited capabilities there. Like you can configure the retries up to 2 times, for example. But with SQS integration, you have full access to the queue, and you can configure up to like 1,000 retries on your stuff. You have access to the queue. You can see its queue depth. So that's the second one, where with async invoke, you actually don't have enough visibility to the backlog or what's happening. If your customer spike all of a sudden, you don't see how much is pending versus how much is executing. While with the SQS triggers to Lambda, there is a full set of CloudWatch metrics that gives you exactly how we are processing, and we're going to see a demo of that soon. You have the queue, such as several features of the queue, like the retention policy you can decide. You can decide what's message visibility, timeouts, several configurations of the queue that you can configure yourself. On the other hand, there is no extra cost for async invoke. Like, we handle all the work for you. But to get all the extra value that you see when you use the triggers, you would need to carry a cost for SQS requests. So you handle that, which is like per million messages, like something like 40 cents. So usually it's not significant on any of our customers' bill. Like a queuing system is just an infrastructure tool that people use in communication between their systems. So these are a list of some of the features that you can use directly when you use SQS triggers to Lambda instead of the async invoke. You can delay the messages for up to 15 minutes. You can use server-side encryption. So if you want to encrypt the content on the fly, you can do that. You can control the retention period. So if you have data that needs to stay for 14 days, you can do that. You can even limit it and allow it to expire in one day. You can purge the content of a queue if you're sending like loads of test loads, and then you decide, okay, that's not exactly what I want to do. You can just go. So you have full access to the queue. Now, I'd like to go and look a little bit under the cover of what we have done with SQS and Lambda. So here we are seeing a queue with lots of messages in it. And I have 3 consumers. I have 3 consumers on your right-hand side, my left-hand side. Now, these consumers will issue a request to the queue saying, give me a message. Once that request arrives to the queue takes that message and puts it in a state called, in an invisible state. So it's still in the queue, but it's invisible for a period called the visibility timeout. And you would hear us and see in our documentation the concept of visibility timeout always listed. Now, the message gets delivered to the consumer, and the queue has decided which message should be delivered. Like, you don't say, I want this stream of messages versus that stream of messages. All the messages are durably stored on thousands and thousands of servers that we have, and we do, behind the scenes, we determine your queue, which nodes it's stored on, and try to be efficient in handing you the messages as soon as we can. Now, if another consumer pulls a message, the queue will hand it another message. Now, let's assume the first one successfully processes this message. What's going to happen now, it goes back to the queue and say, I acknowledge that I have successfully processed this message. Go ahead and remove it from the queue. The second consumer comes and says something broke down. I couldn't fully process this message, internet connectivity issues, my downstream dependency was down. So the consumer in this case doesn't need to do anything. It just doesn't need to acknowledge and delete back the message. And that message is still on the queue. It will wait for this duration of visibility timeout that you can configure yourself, and then it will just appear back on the queue. And it will be ready now for another consumer to come and pick that message. Now, how does that visibility timeout actually works? It's a configuration that you set on the queue, and you say, I want it for X seconds. When a receive message call comes, if the message is not invisible, it will be returned for you. Now, if you call receive message again, you wouldn't receive the same message. You might receive other messages, but the one that got marked as invisible will stay hidden, and you will not get a replay of it. If that visibility timeout expired before you acknowledge the deletion, we will end up delivering that message again to you. We will just replay it back. A couple of concepts here. When you send messages to SQS, Lambda would open a long poll to your queue that you've configured to trigger the Lambda function. And that long poll is very powerful because the way long polls work, you can configure it to wait up to 20 seconds, but it's an active connection that is always. The moment a message arrives in your queue, that long poll terminates, and it returns the message for you. So it's what we favor here with long polls is we prefer that the messages are delivered versus delivering the full batch. So there is a trade-off here. We prefer to have the messages always delivered. So the long polls are always open. They are waiting for 20 seconds. The moment there are messages in your queue, those will get delivered. And that has been a source of confusion sometimes, because when someone goes and configures saying, OK, I want to configure for 20 seconds, we've noticed that some people got confused and thought, oh, the receive will wait for 20 seconds until it terminates. No, it doesn't. It will terminate immediately the moment there are messages. So now let's assume that you've got a load of messages coming in. What would we do on the Lambda side? What's going to happen is we start with the 5 concurrent requests against the queue. So we will launch 5 invokers that will constantly pull from this queue. When your traffic increases, we start increasing the number of pullers that are going against the queue. We increase the number of pullers, and we increase the number of threads. On average, roughly, we increase that by a rate of 50 pullers per minute. So if you get all of a sudden a high spike, like you have a popular product that goes on sale, and you expect lots of traffic coming to your site, you can send all those messages in the queue, and you will see quickly that your lambdas, the number of invocation for your lambdas, is just going up as it scales up. And I call this the auto-scaling for the serverless world, because now I've kind of did my decoupling. I have my buffer sitting in the middle, and the Lambda is smart enough to determine when I go up and when I'll go down. And we'll look at multiple signals. We'll look at your queue depth. We'll look at how many messages are being returned from a call to determine what do we scale. Now, what happens if I hit my limit on Lambda and I get throttled? There is a concurrency configuration on Lambda where by default it's 1,000 on your account. If you reach that 1,000, or you can go and configure it and just say I want 10 executions of Lambda only, then what Lambda would do, it will throttle on the poller. We will go and check, is there enough time for me to re-execute another function here? And we'll do what we call it an internal retry, where if the visibility timeout is larger than the function timeout that you've configured, we'll go and execute another function, do a retry. Now, what if that call fails? If that call fails, that message will go back in the queue, and it will go in that invisible status until we replay it back. But in this case, we're going to increment the receive count of the message. So you will get a sign that, oh, the message has been received once, the message has been received twice, and you can configure your dead letter queue to say, well, maybe after 3 times, I want that message to be routed because there could be a problem in the message itself or in my downstream dependency. So now I know all of you now are anxious and would like to see maybe some code. But in the interest of time, I tried to record most the code here so we ensure that we're on time here. So I'm going to start by, first of all, I go to the SQS console. I create a queue. I can give it any name I want. So reinvent queue. We can choose between a standard or a FIFO queue. And then if I scroll down, I get to configure my queue. Now, when I configure, what are the things that I configure? The first one is my visibility timeout. I'm going to choose 5 minutes or 300 here. I'm going to also decide what's the long poll and always use long poll. So I use the 20 seconds for my long poll. I didn't configure any of the server-side encryption now for the purpose of this demo. Then I'm going to go to my Lambda and create a Lambda function. I have a couple of options here. I could either from scratch or use a blueprint. Just give it a name. And then I set an execution role. Here I have pre-baked a role that has enough access to pull from my queue. That's pretty much all what you need, is to be able to pull and delete from the queue for that role. Now I have my Lambda. I have some code here that I'm just going to put in. And in this code, what we are doing is we pull the records. So there is a data structure here that we have it fully documented. And I loop it through all the records that I have received and just display a message saying we've successfully processed this message. Then I'm going to go and set my timeout on the Lambda so it doesn't expire very quickly. One of the things I put in this function is a delay of 100 milliseconds. So it just slows down a little bit. So I made my Lambda concurrency for 1 minute. I can configure also how many instances I want to run with the Lambda, and I left it open so it can go to the max concurrency limit. Now here I can just go and test that Lambda whether it's correct, and there is a template that I choose. If I test that template, the SQS template, here I go and I see what I have logged, which is like I successfully processed one message in my batch. So I've sent a message. I didn't send it yet through the queue. I just sent it directly to the Lambda to ensure that my code will successfully process it. Now comes the next stage where I want to connect my queue to it. So I've chosen a queue called the reinvent queue here. I configure the batch size of 10. Then I add that trigger. Now, once I've configured this trigger, now the pullers are ready. They will start looking at the queue and start seeing what's the depth, what's the correct scale for me to process by. If I go to my code now, and I want to push some messages into this queue. So I use the reinvent queue here. And then I put just some simple code where a message, a hello world message, I'm going to send it out. I create a message request for SQS. And I say, go ahead and send this message. So I'm going to just run this instance. And what we see here is there is a counter that is going on saying sending message 1, 2, 3. I'm going to launch 5 of these at the same time. And we will start seeing that producer just publishing messages. So I've got now a few of those producers running all at the same time. Each one of them will start pushing messages as fast as it can, as fast as its kind of local internet is allowing me to do. So there are now 3 instances, and now I'm launching my 4th one. It started to send messages. I have now a stream of data just bombarding my queue. Now let's come and look at what's happening here. And the first metric I'd like to point your attention to is this message in flight metric that is on the queue itself, that you see it in the table. And that message in flight shows how many messages are currently being processed. The word in flight is we use it for the messages that have been pulled from the queue and currently is being processed. So you're working on these messages. That's why they are called in flight. Messages available is your queue depth, is how many messages are today in the queue. And we see that I'm not building any queue depth, but my messages in flight has been around like 5 or 6 instances of that. What I'm going to do now, I'm going to go to my Lambda function, and I'm going to induce some delay in it. I'm going to make it take 10 seconds to process my function. Let's assume I have a larger load. So I make it to take 10 seconds to process. What this now will do, this will apply a back pressure on the pullers, and the pullers will say, oh, some queue depth will start building up for me here, where we are seeing the mouse. So what I'm going to do, I'm going to start having more pullers to pull from this queue. So we'll see now the number of in-flight messages has jumped to 340, and it's just going to keep going up until it reaches a state where it's chewing through this backlog. So we are seeing some backlog is being built. And here we see on the number of messages received, that more pollers are now getting messages from the queue. And you see this sharp jump once I configured my producers to send messages. Different metrics I can look at: number of messages not visible. This is the number of messages kind of sitting in the queue that you cannot access. They have been already processed. Those are the in-flight messages. So as we look now, the backlog has got to a stage where it's being worked on. The number of messages available is going down. OK. Uh-oh. The video stopped. So what we see here is that the number of messages available has went down, while my number of in-flights has reached the maximum, the maximum to access. And we've seen kind of the pollers are going up, the queue depth is going down, and that's how we scale to allow working on this code. The next scenario I'd like to talk about is, what if I have a downstream component that can't handle this infinite concurrency, that can't handle like 1,000 processes at a time handling it? Like, I could have a relational database where I have a lock that I have used. I don't want multiple instances from that running at the same time. So I want to control that concurrency. And in fact, here, as I was talking to Rory yesterday, Rory chooses her dresses in a very, very unique way. She has a concurrency of 1. She can wear 1 at a time. She can't wear more than that. But she keeps a backlog of 4 or 5 in her closet always. So she lambda-sized, as she called it, her.
I may have taken this whole serverless thing a little bit too far. Because I was looking at my closet, right? And 99% of your closet is, well, sitting idle because you could only wear 1 outfit on a time. So I started thinking, well, why am I paying for idle clothes that I may get to wear? I know, it's a little crazy. So I rent my clothes. And I get a concurrency of 5 things at a time. And I don't do laundry. And they ship to my hotel, so I don't do packing. And I'm an extremely lazy person. So now I don't have to buy clothes. I only pay for what I use. And, well, all of the patching.
So if you're writing the software that delivers
everything else is taken care of for me.
If you're writing the software that delivers to Rory's closet, you need to make sure that you don't send her more than 5 at a time, because she's not going to accept that. So what we do in these cases, if we have, as an example, Rory's closet at the end here, demonstrated as a relational database, you can't put more into it at the same time. You want to control your locks in it. The messages go in the queue, the Lambda pulls, and then you want to control how much traffic is going there. So you have a picture that looks like this. So on your left-hand side, you're seeing a spiky traffic coming to your website, or you're putting something on sale. But downstream, you want that to be controlled. You want fewer messages, fewer instances are being processed at that time. And that's what we call it with limiting concurrency. And here, what I'm going to do, I'm going to actually switch to a demo, to a live demo, and just show how we would do that. The demo? Yeah, that got my screen. So here what I have, I actually have, that's the live demo I just showed through the presentation. So I left it running before I start this meeting. And what you would see here is I'm sending like 60,000 messages, and the counter is going. There are 5 instances of that is now sending messages at the same time. And if I come to my queue and we just do a refresh here, we'll see that we have 650 or 850 instances are running. So 650 instances are running, and at the same time. So those are the number of messages in flight. But what surprisingly here you look at is it's 0 depth of the messages. Like my Lambda did literally scale to all these producers that are that are currently running, and allowing me to process 650 Lambdas at the same time. I'm still not close to my full concurrency limit, but it did that for me. So if I look at some of the graphs here, if I look at the number of messages sent, that's what my producers are publishing. I stopped it a little bit and came back while I was setting up the demo, but before we walked into the room, so this is how many messages we are sending in the queue. If we go and look at the number of messages received, we see that we have a jump in those as my Lambdas is scaled to it. And if we want to see number of messages that are not visible, here, this steady stream is all the messages that are currently in flight. So my queue is actively working now as we talk. So what I'm going to do, I'm going to go to my Lambda. And we see here all the invocations and all the stats that you could see about your Lambda invokes. But if I go to my configuration on the Lambda, and let's do some live code change. So the last thing we said is that we induced a delay of 10 seconds. So what I'm going to do, I'm going to say, I want to keep this 10 seconds, but I want to go to my Lambda concurrency down here. And I'm going to reserve a concurrency for it, which is how many dresses Rory's closet can take. So now we have 5. Oops. Sorry. I'm going to just do 5. I can't type even 5 here. So we'll save that. Now, what do we expect to happen? We said only 5 are allowed to appear here. Lambda is going to react to this immediately and say, I'm going to limit this concurrency of this function to 5. So it's going to start taking down the number of pollers. And what we would see here, let's go to our queue. It's going to take a minute until those metrics arrive. So I'm going to just talk over that until I can consume a minute here. What you would see is that the number of messages let's refresh here. We'll see a backlog started to build up immediately. So messages available all of a sudden jumped to 2,800. And the messages in flight dropped to 118. So all of a sudden now I have less pollers that are pulling from this queue. And my queue is building a backlog. So Aurora's dresses are coming somewhere to a warehouse. She keeps doing those orders, but she doesn't want them in her closet. Only a few are arriving to the closet. Now here we have 118 because we are receiving messages in batches, so we can have 5 instances. Each of them is taking 10 at a time. We're processing roughly about 10 per second, 6 per minute. So that's how roughly we get to this calculation. Don't go very accurate numbers, but this is what's happening behind the scene, in fact. We're going down into our number of pullers and ensuring that now the backlog is being built. All of a sudden, I have now 6,000 messages being built. And if I go to the number of messages not visible, here we see that an immediate drop happened to my number of in-flights. And what we can do now, let's assume, OK, a backlog has been built. I can go to just my sample code and just terminate those pollers. I don't need them anymore. This will enable me to chew pretty much through my. So I just terminated 5 instances here. I don't need them anymore. This will reduce now the number of messages that are being pushed into my queue. But meanwhile, let's take a look at what happened in the Lambda side for this. So if we go on the Lambda side and we look at the monitoring tab, we'll see an interesting aspect here. And the one I want to point you to is the throttles one. So let's make this just 1 hour. which is the time of this session, we see the number of invocations was going at a steady state. But once I induced this limitation of 5 concurrency, the Lambda immediately started to throttle and saying, I can't process more, do something about that. So Lambda now throttled. Now the pollers are smart. They will react to this signal, this throttling signal, and say, OK, no more messages I need to pull from this queue. I have enough to process. I'm going to process those until we finish and chew through that backlog. Now if I go to my SQS console and look, so we used to have 6,000 messages in it, but we are still processing with the 5 minimum 5 concurrency that we've set on Lambda. So if we refresh here, what I'm going to expect to see is that my messages available have had a little bit of, it's not really yet a drop because there are more messages coming in the queues. So, but in a few minutes, we'll start seeing we're chewing through this backlog. But what's interesting is the messages in flight has dropped quite significantly from the 600 to 800 number. Very closely, we see now only 50 messages that are in flight, which is roughly, you can say, 5 concurrent instances times 10 per batch, because my backlog is full, so I'm receiving 10 at a time. So that's the demo here that I really wanted to share with you about kind of that illustrates to you as you see these metrics and you interact with this integration to understand, well, what's happening behind the scene? Why all of a sudden I have more receives versus less receives? So try to just visualize like what's happening behind the scene on the implementation side, and that will give you what we have done to achieve this auto-scaling behavior. So I'm not going to play this video because we've just done it pretty much live. Once I stop my processor and like it starts chewing through the backlog, what you would notice is the number of sends has dropped to 0, which is why I stopped my publisher. And it's chewing through that backlog. All the messages have been dropped. We've seen that how the in-flights went to 0. And then if we look at, so this is the send. I stopped the senders here. There is no more traffic coming in the send. If we look at the receive side, we see that the receive actually went for 1 second, went to 0, because there were a bunch of messages that are still what we call it the internal retry. We've received those messages, but we can still re-execute more lambdas. So we stop receiving from the queue. We go execute those lambdas. And that pretty much allow me to continue consuming through that queue until I finish all the messages. And one thing we heard from our customers is that we used to have 5 minutes metrics on SQS, and that has been limiting the time you can react to these signals or to the CloudWatch metrics. Like, you want to react faster, and I'm pleased today to announce to everyone here in this room that we've just launched the ability for you to view 1-minute metrics on SQS. So that will give you more precise, more accurate review. And this one, I just got it as a screenshot from the demo I was running that tick. So you can see the delta between one point and the other is literally just 1 minute. So that gives you more control over your queues. Thank you. And that's not enough. We've also heard from our customers that they used to be able to just configure standard queues for SQS, but they couldn't configure FIFO queues, first in, first out queues. And I'm pleased also to say that FIFO queues are now available for you to use as well to trigger lambdas. And this one is very powerful. So if you have a business entity that you want the transactions on them to be sequential, but still get the high scale of a queue, you can do that. One of our customers uses FIFO queues in their data center. Comcast, in fact, Comcast uses FIFO queues for their data center. They have a lot of data in their call centers, sorry. They have lots of call centers, but when you call a call center, you can do multiple modifications to your account. You could say, add this package for me, remove this thing from me. You want that set of transactions on your account to go in sequence. You still want them to be queued. So you want to keep the sequence for one business unit. In this case, it's the account number that I am dealing with. But for the rest of the queue, I don't care. I can process them at any rate I want. So hopefully with the launch of the FIFO triggers, you will get that. A couple more tips here. We have Amazon SNS allows you also to trigger Lambda, and SQS allows you to trigger Lambda. And sometimes we give you kind of this toolbox of tools in it, and we say, here you go. You can trigger Lambda with SNS. You can trigger Lambda with SQS. And you're on your own with that. Choose the one that works for your business. There are some differences between which one I would choose if I am going with my. Each one has valid use cases to do. So both of them scale infinitely, the way we've seen the scaling for SQS. The durability, in fact, SNS uses SQS internally to store. So it takes the messages when you publish the SNS. The architecture actually stores those messages using a queue. So you get pretty much the same durability across both with 3 copies of every message that you publish. They are distributed at a minimum of two AZs. The consumption model is slightly different. SNS uses more of a push model. So it pushes these publishes to Lambda. And or the receiver, once that receiver receives the message, it says, OK, I am done. I received my 200. I'm going to get rid of that message. SQS has this acknowledgement component to it, where I sent the message, I processed my Lambda fully, and then when the processing is done, I'm going to say, now it's safe to remove the message. So think of what's the best consumption model. Do you just want to fan out and send the messages at any rate? Or you want actually to get that guaranteed acknowledgement in your choice? And then you can assemble those together. Like you can have SNS published to SQS, then trigger the Lambda, which has been a common pattern that we've seen our customers do. On the retries with queues, you can configure like a retention period of up to 14 days, and that message will keep redelivered for those 14 days. If you have some server or some component that is down and you're not using it, it's not working, you can leave the messages for a while until you can. And in fact, with the Lambda scenario, you can just go to the event source and disable that. Just say, disable that event trigger, so messages will accumulate in the queue and no further processing is happening. Then you can go and enable that. This one is my favorite in terms of tips. As you're working with the SQS and Lambda, in the low concurrency scenario and the high duration function, like the one I used was like a 10 seconds example for the duration, and I still wanted to make sure I don't send Rory so many packages of dresses that she can't just put in her closet because she gets annoyed.
You're obsessed with my closet.
Yeah. So with those, we go set the visibility timeout to 5 times the function and duration. So if to allow for retries, to allow for the time to invoke and the time to process the messages. So what I would recommend is set the visibility timeout to 5 times your Lambda function duration, and that will allow you to essentially not see the messages go back to the queue or the receive count being incremented. Always check that your visibility timeout is greater than the function duration at the minimum, because if the function duration is less than your visibility timeout, we will say, oh, we didn't receive an acknowledgement for this message, so we're going to replay it back to you. And you will get a duplicate of that. The errors that you return from your Lambda, we've seen an example on the throttling ones, but any errors that you put in your Lambda will act as a back pressure to our pollers. So we will see, oh, this function can't process the load, so we're going to use those errors coming back. If you're not successfully acknowledging the messages at the rate you're receiving them, we'll start reducing the number of pollers that are pulling from the queue to sort of give you some relief to process the previous one. throughput and number of invocations are not equivalent. Like, think of the throughput because you have batching involved. So number of invocations, and some invocations could have 10 batches in them if you have a busy queue with a backlog. Other invocations could have just a single message in them. So be aware of that. And the last one, which is not on the slide, is the FIFO one. You can use FIFO for deduping as well, because FIFO has that feature where you can provide your dedupe ID and deduplicate the messages and not enable the execution of the Lambda for the duplicate message. I still highly recommend that your code always knows how to deal with duplicates, because the very minimum case is if I fail to process a message, we're going to replay it for you. So you need to safely make sure that your components downstream deal with a message that gets replayed to you. And with that, I think we are pretty much done here in terms of presentation material. I hope you've learned something new here.
And while we're not going to open it up for Q&A in this room, Lue and I and Stefan will be out in the hallway. We'd be more than happy to answer any questions you have about SQS, Lambda, and why they're better together.
Yep. Thank you very much.